Hello, Physics 2 people. In this video, I want to describe wave equations, what they are, and maybe some general properties of their solutions. And I want to focus in on 1D wave equations and their solutions in more detail, because those are going to be the most relevant to the kinds of waves we set up in electricity and magnetism. So in general, I guess the linear wave equation is given as a partial differential equation, and kind of motivating what it is, think about what happens with a wave. When you have a wave, something like this, and it moves to the side with some velocity v, if you think about it, so the wave is here, and then later on, the wave is over here. So the peak has shifted. So what you might notice is places where, so basically what you're going to get is some sort of relationship relating the curvature, the spatial curvature, to the rates of changes, or in fact, it's going to be the second time derivative. So that basically places where there's a lot of curvature are also going to be places where you get lots of time change, and vice versa. So in particular, the way we would kind of codify that in an equation form is in the wave equation, which states in general, in higher dimensions, it would be 1 over the velocity squared, the speed squared of the wave, times the time derivative squared, minus the gradient squared acting on a general wave. Let's just call it W for wave. And it's generally a function of x, y, z, and t. So in general, it's quite a complicated equation. And this wave could either be a scalar wave, like sound or pressure waves, or waves on a string, or it could actually be a vector wave, like light is going to be. So this is the equation this is called the wave equation. If you're thinking about, or some of you have heard about Schrodinger's wave equation, it's a little bit different than this. It's not a traditional wave equation. It actually only has first order time derivatives, and it also has imaginary numbers. So it's a little bit more complicated, and we won't talk about that in any more detail. So this is the general wave equation in 3 dimensions. Let's focus on a 1D simplification. Okay, so the 1D wave equation would be written as 1 over the velocity squared times the time derivative squared minus the spatial derivative squared. That combination of derivatives acting on the wave, and I'm going to call the solution in 1D just some function of x and t. So what this could represent might be, let's imagine that I have x, and what I could imagine, it could be maybe the height of a violin string as a function of x. So you could imagine that the height of this violin string could change as you move in x or time. It's called a 1D wave because it only propagates in one spatial dimension. Okay, so it is true. So in 1D, we can write down the most general solution to this equation. So the 1D wave equation is 1 over v squared times the second time derivative minus the second spatial derivative acting on a function of x and t equals 0. And we can show that an arbitrary solution to the wave equation can be expressed, and we say that instead of being an arbitrary function here, to be a solution of the wave equation, it must be built out of the combination x plus vt or f of x minus vt. This represents a wave. So if you think about it, evaluate this at time equals 0, you get some profile f of x. And then as time increases, you're adding to the argument, which means this is a wave which moves to the left. This is called a left mover. Whereas this would be a right moving wave. Okay, so both of these, in fact, you could take an arbitrary sum of them too with constant coefficients, would solve the wave equation. And so in general, you can have the general solution could be some, I don't know, we could call it, let's write it as the L for left mover of x plus vt plus r, the right moving solution, x minus vt. Let's see how that works. Let's take, let's plug the right mover into the wave equation. Okay, so let's evaluate 1 over v squared dt squared minus dx squared on the right moving wave. The way we see that this works is that what we're actually going to do is define this combination, and let's just call this x minus. It's a new variable, x minus, where x minus is defined to be x minus vt. And what we see is that partial derivative with respect to time can be written as the same as minus 1 over v partial derivative with respect to x minus. And similarly, a partial derivative with respect to time squared is really the same as minus 1 over v squared partial derivative with respect to x minus squared. Similarly, for partial derivatives with respect to x. So we can rewrite this as 1 over v squared oh, I have my v's upside down. Oh, God. These were supposed to be upstairs. You just have to go through the chain rule. You get v upstairs, v squared upstairs. So this becomes v squared. You can replace when acting on this combination, a function of this combination, a time derivative may be replaced with v squared dx minus squared. That's the first derivative, minus, well, an x derivative is the same as an x minus partial derivative. And what we see is that in fact this is just zero. This differential equation just explicitly evaluates to zero when acting on a function of x minus alone. So we see that this function solves the differential equation. The proof that the left movers solve the differential equation is very analogous to this. All right, so that's one thing. The fact that we can have both left and right movers kind of allows for, you might think that you can, well, so you can have both left and right movers, I'll just say it that way. And it turns out there's a special family called sinusoidal solutions. And for those, we just make a general ansatz. We're going to guess, say that the right moving sinusoidal solution is just going to be some amplitude times sine of, and we'll go ahead and say some number k x minus omega t. Now, this is supposed to be a right mover. So let's specify some names here, I guess. K is called the wave number. Omega is called the angular frequency. And you might think that these are just going to be arbitrary coefficients or arbitrary numbers, but what we actually find is that in order to solve the differential equation, so we can plug this into the differential equation and we get the following relationship. The time derivatives give us factors of omega, so we get 1 over v squared times omega squared minus, we'll have r naught sine kx minus omega t plus k squared times r naught sine kx minus omega t equals 0. So that's what I get when I plug it into the wave equation. Kind of factoring that, I see that omega squared over v squared minus k squared, and then I have, there's an overall minus sign, I get r0 sine of kx minus omega t equals 0. And okay, so to solve the differential equation, you actually end up with a constraint on the parameters omega and k. R naught can't be 0, because if it was 0, the whole solution is 0. And so we must have that the speed of the wave squared equals omega squared over k. Or turning around, you could say v equals omega over k. So we learned that you can't have just any angular frequency and any wave number. The ratio of the two are constrained to be related to the velocity, or the speed. Just some comments about interpreting this. So we have a wave, which is like, so we have a right mover, which is like r0 times sine of kx minus omega t. So this is going to be periodic both in time and space. So if you draw, say at t equals 0, some snapshot in time, what you would get is a graph, it would look sinusoidal. The amplitude would be given by R naught, and you would actually get a wavelength, a distance from peak to peak at this snapshot. The wavelength is equal to 2 pi over k. So the wave number is inversely related to the wavelength. So the larger k is, the larger this coefficient is, it means you basically need to make smaller steps in x to get a repeating pattern. So the wavelength is smaller. So the bigger the k is, the smaller the wavelength. Similarly, you can do the same thing in spatial directions. You can say at fixed x, then you can graph your function and you would get, now time is on the axis, and you would write for the right mover, we would get a sinusoidal graph. Again, the amplitude is going to be R naught. And here, the distance from peak to peak is not going to give us a length, it's actually going to give us a time. It's the period, and that's going to equal 2 pi over omega. Or sometimes we write that as just 1 over the frequency, f. And our relationship that v equal omega over k becomes the same as lambda over period, which makes sense on unit grounds. The speed equals the wavelength over time, or frequently it's written as lambda times f. That's another way to write the same relationship. So these are our key equations when you have waves. It relates the wave speed to the frequency and wavelength. What you see is that the same wave equation has many, many, many solutions. Okay, you have infinitely many solutions. The only constraint is that you must relate the wavelength and frequency so that their product gives you the speed. And what you see is basically small wavelength corresponds to large frequency, and large wavelength corresponds to small or low frequency. All right, but any combination of, or any value of lambda is allowed, any wavelength is allowed, or any frequency is allowed. You just have to make sure that the product of lambda times f equals the speed. We can pull this all together. The right mover then can be written as the sinusoidal right mover. We can write it as so I'm just factoring out the wave number k, and using the relationship to the speed, I find that sure enough, for just the right values of k and omega, or lambda and f, I can write this as x minus vt. So as long as, so this is if, you constrain these to have the right relationship. In fact, even though it looked like it was an arbitrary combination of spatial and temporal oscillations, It actually was finely tuned so that you only really had the right moving combination appear in your expression. Finally, one last little observation. When we go to talk about intensity or power in a wave, the intensity or energy density typically goes like the wave squared. So we're going to see a similar kind of thing happening in with electricity, with electric waves, with electromagnetic waves. I just didn't want you to be surprised when that pops up. Okay, so that's kind of a crash course in wave phenomena. We're going to apply many of these same ideas to electromagnetic fields and find wave solutions to those equations.